So this video is about functions. We're going to use functions and lead into talking about graphs. That's the short version. And I want you to be able to distinguish between a function and a graph. In particular, an equation and a graph. For instance, if I were to write y equals x squared, a lot of times I'll get, oh, y equals x squared. That's a parabola. Or y equals 2x plus 3. You say, oh, mx plus b, that's a line. Okay, that's kind of true, but it's really not true if we're going to be strictly speaking. Because this is an equation. A line looks like this, a parabola looks like this doesn't look like that, this is not a parabola. This is an equation, and if you draw a graph to help you think about this equation, then it would wind up being a parabola, and I'm going to describe to you more in depth what I mean by help you visualize it. Okay, so let's start talking about functions. The first thing about functions that we need to address is that they have inputs and they have outputs. You put something into a function and something comes out. Okay, that's not it, but that is a big part of it. So let's talk about going in, coming out. Alright, so let's say, this is my favorite analogy. I like analogies. This is my favorite one for functions. It's factory. It's not the best looking factory. Okay, this factory makes smoke. Sorry. And this factory could make anything. The thing that always comes to my mind, because it just popped in my head one day, and because it's easy to draw, is a table, a wooden table. So into the table factory comes wood. So let's say we just got this stack of lumber that comes in to the factory. Right? There is some wood, stack of lumber. Comes into the factory. Saw blades whirring and hammers hammering, and out comes a wooden table. Okay? Fairly simple concept. In goes wood, out comes a table. And that's input-output. Alright? So, I don't even want to get into exactly a function yet. I just want you to understand input-output. Something goes in, there's a rule for what happens inside there, and out comes the thing. Okay? So let's take that idea, and let's move it into some numbers. Let's make a factory that works with numbers. Okay? So, again, a factory. Should have this copied and pasted or something. But here's another factory. The smoke's a little lighter on this one, goes into the air. Alright, so let's say this is an x plus 2 factory. Okay, so in goes an x, and out comes x plus 2. So let's look at some examples now that we can look at examples. In goes a 2, and here takes a 2, adds a 2, and out comes a 4, right? In goes a 7. The 7 goes in, saws get going and start hammering, and out comes a 9. Just takes a number and adds 2 to it. Alright, so let's look at another one, and I know you've been enjoying my fine art mastery, but we're going to have to make it a little simpler. We'll just draw a box, okay? Maybe a smokestack. Okay, so let's call this the x squared factory. Okay, just getting the ideas of inputs, outputs. In goes x, and out comes that x times itself. That's it. In goes a 2, out comes a 4, because 2 times 2 is 4. In goes a 7, and out comes a 49, because 7 squared is 49, and so on. Alright, now, you get the idea of input-output. Now we're going to highlight what's very special about a function, because lots of things have inputs and outputs, but not all things are functions that have inputs and outputs. Let's say that we have this factory, and it's the square root of x factory. In goes x, out comes the square root of x. And remember, the square root is some number times itself, you get x with that number, okay? Let's look at an example. Let's look at 4. Nice example. Because you say, hey, 2. 2 times 2 is 4. But remember that negative 2 times negative 2 equals 4 as well. Negative times negative is positive. 2 times 2 is 4. There you have it. Well, what should this factory make? Should it take a 4 and make a 2? Well, it could. It would work. That would be the square root of 4. But it could also, with the same input, create a different output. Okay? Now, like, these guys in here need some special directions as what to make out of this 4. Okay? There's no hard and fast rule, what's supposed to come out of here. So, that's the problem. That's not a function. A function knows what it's supposed to make. Whatever comes in, there's no question. Only one thing's going to come out. Okay? So, this is not a function. No, sir. So, a function has inputs. It's I/O. When you see that, I/O means input output, right? Has inputs and outputs. But also, so we don't have this situation going on that we had with this square root of x factory. For every input, there is that even a word? ER. There is 1, which means there is 1, and only 1. Not only is there 1, but there is only 1 output. Okay? So, that's what I want you to start to see. The first thing that I want you to see is that the function is defined as something that has inputs and outputs, and for every input there's one and only one output. That's pretty basic stuff. Okay? So, of course, in math, we are interested in functions that use numbers. Not just any old function, but functions that use numbers. So, let's look at one. We actually had one earlier. Y equals x squared. Alright. So, let's say somewhere in history, somebody was interested in all of the possible numbers that could solve this equation, right? You could put in a 2 and you would square it, you get out a 4. You could put it in a 3, square it, you get a 9. You could put in a 1.25 and you get out a, I don't know, 1.125. Somebody check that. I think that's right. So, 1.625. You should really look that up. But anyway, you can put anything in for x and get whatever the result is out for y. I could put in a negative 2. I would get 4, positive 4. So, how can we track all of these? It's just, I've named a bunch, and you probably, I don't even know if you remember one of them, but you've probably forgotten at least one of them. So now we could draw a table. This would be a good way to keep track of some of these things. So I'll put in a 1, and the result is 1. We're just going to keep track of all these things so we can look it up later, maybe. So we'll put a 2 in there. We'll get a 4. We'll put in a 3, and we'll get a 9. We'll put in a 4. We'll get a 16. Maybe we'll throw some negatives in there. Negative 2. Negative 2 would produce a positive 4. Negative 3 would produce a positive 9. So there you go. We started to track them, but several things are not good enough about a table. What about everything between 1 and 2, and in between 2 and 3, and you know what, we forgot 0, we should have done that. So not only do we want to expand this more, and we can see this is going to take up a lot of room, we also want to see what happens between 1 and 2, what kind of stuff is going on in there. Apparently there's all these numbers between 1 and 4 that come out. So here is where Descartes, he proposed one day that rather than say a table, and I don't know that he proposed it as an alternative to a table, but it seems a logical progression to me. He said instead of maybe just writing them down, saying here's one, and related to the one, we run one through this function, you get out a one. He says, well, let's just draw two lines like this, and running along this line, we'll put some numbers. We'll put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on forever. And let's, this is 0, so if we go the other way, let's just go negatives, okay? And let's do the same thing here. We can represent a whole other set of numbers go in this direction. All right? There's some right there. And he suggested this because he liked it, not just because he wanted to make up something for math class or something. It was a big breakthrough. Everybody thought it was great. Okay? So now, instead of writing 1 and 1, which takes up a lot of space, a big thing about looking for solutions and keeping track of data is having it take up less space. You'll find that in computers or whatever you're looking at, taking up less space is always good. So look at all the room we took up with this, and how much room this takes up, and look how much room this takes up. Just a dot tells me that for this function, if I put in a 1, what I'll get out is a 1. And how about 2? If I put in a 2, this graph will tell me that I will get out a 4, and I know that that's what I get when I put in a 2 in this function. I get a 4. When I put in a 3, I'll get a 9. So 4, 5, 6, 7, 8, 9, sort of. Okay, and this is what Descartes was saying. He was saying, this is awful. This is 2. This should be where that is, and this should go away. This is bad. All right, and we'll pretend like that's dust. And okay, so then this is up here at 9. Okay, that's all our graph is. And now we can go back and say, oh, I forgot to say 0. I was curious about that. Put in a 0, square it, you get 0. Go to negative 1, you're going to get positive 1 when you square it, and so on. You come over to negative 2, you get positive 4. Okay, these equations, like these, are not related to these shapes. This is a parabola. They're not related in some random way. They produce these shapes because we're tracking the solutions. So then we kind of draw some conclusions that there's this kind of a pattern between each of these. That's pretty bad. These whole numbers, and I'm just going to connect them nice and smooth. Now I can kind of see what's going on. Like, say I want to go to 1.5, that comes up with somewhere around almost 2, That's what's going to come out of this function when I put in a 1.5. That's what a graph is. That's why we graph things. Alright. Let's look at another equation, the one we just visited, where we have the square root of x. Remember, we had that factory. And so in goes x, it gets square rooted, and it comes out the doors as a y, So I could track all of these. I could say, here's my x, and here's my y, and in goes a 4, out comes, well, remember we said 2, but also a negative 2, and the way we write that is I could have a positive 2 or a negative 2, plus or minus 2. Let's do it for 9, that's a plus or minus 3, and so on. So what happens on the graph when we try to track all this stuff, I'm going to try that again. When we try to keep track, oh, that's much better. When we try to keep track of all these answers, we mark off some stuff here, we mark off some stuff here. Okay, so let's say I go out to 4 on the x-axis, right? We're gonna run into a similar dilemma that we ran into up here at the square root of x factory. The guys in here are saying like, well, with a 4 I could make a 2 or a negative 2. Which one do you want? Okay, and that's where we ran into not a function. And that's what we're going to look at here. I go to a 4. Okay, 1, 2, 3, 4. Well, where am I going to put the dot? I could put it here. because that's one possibility. I could also put it down here. I could put it at -2. What do you want? And that's the problem. We have to. There's no definite answer. There's no definite output. There's this question. I don't know what I'm supposed to do. Okay, let's say I come out here to 9. 5, 6, 7, 8, 9. Perfect. And we say here we are at 9. What's the output for putting in a 9? Well, it could be a 3. That's a possibility. That would work. But completely just as valid is -3. Alright, +1, I could do +1, I could do -1. The only one with one output is 0. Okay, so let's draw this. Let's make some conclusions in between each of these. Draw a nice smooth curve. And draw a nice smooth curve there. Nice and smooth. So here's what happens. You have these inputs, and for every input, there's more than one output. Okay? Even if that happened for one of the inputs, we now have this situation where you gave me an input, and I wasn't sure which output I should give you. You see what I'm saying? You have two valid outputs. And if you have two valid outputs, you don't have a function. Okay, and it's just a definition. It's not something that fell out of the heavens. It was defined. And this goes against the definition of a function, right? It has inputs and outputs. There's that first stipulation, but that second one, the one and only one thing, right? There's one and only one output, that part. That doesn't exist here. There's several outputs, lots of different times. Even if it happened once, that'd be bad enough, but it happens almost every time. So that's our problem. And you'll notice now, something I'd like you to really bring your attention to is take a look at when you have those two outputs. That means that right here at, say, this input, right here at this input, you can look above it and find an input. You can look below it and find an output, another output, two different outputs. So there are two outputs that are directly, above and below each other, right? And I could draw a line between those two outputs. Okay. Now, this may be bringing up a memory. I draw this vertical line. It touches my graph, the graph that represents all the solutions to this equation. It touches that graph more than once. Since it touches the graph more than once, in any place, if it happens once, if this vertical line touches the graph in two different places, even one time, it's nullified from being a function. Because at some point, you throw something into the factory, the guys in the factory aren't sure what to make out of it. They could make 2, 3, 4, 5 things. Okay? So once the guys in the factory aren't sure what they're supposed to make, this is what it looks like on the graph. It has something up here, something down here, not necessarily above and below the x-axis, but they are, up and down of each other. And you could draw a vertical line and hit both of them. That is the vertical line test. If I draw the graph of a function, and once I have that graph, if I can draw a vertical line and hit it more than once, that means it's not a function. That's the vertical line test. Alright? So that is going to wrap it up here for us with functions and inputs and outputs and graphs of functions. Okay. One last thing I guess I would add on is just a word. If you have a function or something you suspect is a function, and it has inputs and outputs, and when you put in something, you get out something, you understand that. You put in wood into the factory, you get out a table. If you're looking at that and that's going on, but then you look at the second part about the one and only one output. If there's multiple outputs, well, it still has a name. If it has inputs and outputs, at least that's called a relation. Okay, so it's just a vocabulary word we should know. A relation is just something that has inputs and outputs. You put something in, and you know that you're supposed to get something out. You know how to get something out of it. Okay. So that's it. I hope this was helpful. Let me know if you need any more help.